Avionics International, a photonics company that holds the core IP for multiple applications you're going to hear about today, and has a very strong partnership with YMK Photonics here in Korea.
Thank you for the introduction. Thank you for the invitation.
It's not working. It's not working.
Stop talking. Okay. Thank you. This is the presentation. Let me go to the title of the presentation. And this is where I'm going to give a little bit of technical background on broadband integrated optical beamformers and wireless networks. Especially if you want to enable all the applications that you've seen in virtual reality and augmented reality, we need wireless networks to connect to all our devices. So first let me start with the company introduction, Lyonics International. We have a background of 16 years in integrated photonics with the companies Lyonics, Satrax, CF Photonics and Ocrolix. And we build up IP portfolio there and the technology and manufacturability of photonic circuits. Very recently, as of April this year, we got an investment through YMK Photonics, a Korean investor, and we are focusing now on the development and on volume manufacturing in our location here in Korea. So Lyonics International, it is a leading global provider of customized microsystems solutions, and in particular integrated photonics based in scalable production volumes. We apply disruptive technologies to solve major societal challenges. In particular, integrated photonics is one of our key enablers. So let me make the bridge then to virtual reality, augmented reality. You've seen it already. Pokemon was a big hit this summer. And this is actually my daughter playing, finding around the corner at our house in the Netherlands, a Pokemon figure. And what does she need to play that game? Well, this is first of all high-speed communication and a wireless network. And that sounds pretty trivial, but we are very fortunate that we have that. We in the Netherlands, you guys in Korea, and that you can play this game. Like finding this object, picking your ball, throw it, and then you have gotcha. I caught you. So what is required for this high-speed communication and this wireless access? Well, it's even more people want to do that. So this is a picture that was taken in Kijkduin. Kijkduin is very close to Amsterdam. And it was a rush of people who went to Kijkduin in the dunes and find all these Pokemons. So all people from all over the country came there to play this game. And it was a big hit. But the locals were not that happy about it, you can understand. So more and more people want this. So how many people want this? Well, if you look at the growth rate of the world population, that is already predicted to grow to about 7 to 8 billion in 2020. And a fraction of that people is using wireless communication, wireless gadgets, phones, tablets, everything. And especially you see the inflection point already in 2008, where there was one wireless object per inhabitant in the world. And it's predicted that in 2020, that will be 6 or maybe even 7, if we grow like we grow now. Which means it's about 50 billion smart objects that are communicating wireless with one another through a wireless network. Well, then on top of that, we are not using only data, but we are also using pictures. Not only pictures, you've seen with the previous speaker, we're sharing video, We're sharing lots of video, the videos become bigger, and we need faster broadband speeds at close to 50 megabit per second with very fast access times, so low latency. So how are we going to solve this? Because what we see is that this data explosion has been growing by more than a factor of 100 over the last 10 years, and it will continue to grow. So this requires a disruptive new technology, and we believe this requires photonics. So what is it, this user experience? Well, I've seen this equation before, but in a different setting. E is equal to mc squared. And in telecommunication, it is the experience of the user counts. And it's going to be provided through a multi-layer system of communication in the spectrum, different frequencies, to guarantee the coverage and the capacity. So how you see this globally is that it is a total infrastructure where you have satellite communication supporting the terrestrial communication. So you see uplinks from the big dish towards the satellite and downlinks towards the local houses, downlinks towards the base stations, and also sharing of the RF signals locally towards cars, moving objects, or directly from the satellite's GPS signals to your objects. So this is a multi-layer, fixed and mobile global network. What you will require is worldwide coverage, and that's obtained through satellite communication and high-capacity networks through the terrestrial communications. 1G, 2G, 4G, now 5G coming. And to do that efficiently, you already see in this picture that you will require beamforming. So you will not be having only omnidirectional antennas where you lose a lot of energy. You will start to do beamforming to point at the position where you want to have the signal. And that is where we want to go. And if you looked at the current infrastructure, you already see that. You see these type of base stations with large array antennas. 3 to cover all the 360-degree area. And they are rectangular to point a little bit in the vertical direction. But they're still fixed. They have a fixed setting, and they're not able to track or to point on demand. And they're really big. See, this is me on top of the roof in Enschede at our university, where also our company is located. These are big phased array antennas, and also supported by dish antennas. So why do we need these high-gain phased array antennas? Well, for the virtual reality, for the experience, for the high-density video, for the online gaming with low latency, for video on demand. And beamforming has already been announced in the 5G roadmap by Samsung in 2013, where they do RF beamforming and predict that that is needed with these type of phased array antennas. And these type of phased array antennas are square phased array antennas, so they can point into directions. So what can we do with photonics then? Well, we need to come to that antenna. And the current infrastructure already has fiber. So we are already in the photonics domain. So how do we get to this antenna? We need to convert from photonics to the RF domain, and that is through our beamforming chip. It is the chip that combines the signals of the RF antenna and feeds it into the fiber. And that is the solution for this game, Pokemon, and to have access everywhere over the globe. And photonics is crucial to obtain that speed and coverage. So looking at more requirements and solutions, we need more frequencies. Yeah, so the current spectrum is full, is booked. We need higher frequencies to get higher capacity. We need better coverage through SATCOM and terrestrial infrastructure. More capacity, so more and larger antennas. Real-time and faster switcher with lower latency. And the high-capacity backbone using different colors of light. That is an advantage that you can do in photonics. I will come up with 3 of the examples, starting with the avionics example. So this is the current solution. I flew yesterday with the Korea Air from Amsterdam to the airport here, and we did not have in-flight entertainment. On some airlines you have in-flight entertainment, which means you have a direct connection with a satellite dish on top of the aircraft to the satellite. And you can do video streaming or emailing or data sharing directly with very limited bandwidth. The current solution is based on mechanical steerable dish antenna. It has aerodynamic drag and it increases fuel consumption. So using a square phased array antenna on top of the aircraft, you can also do satellite communication with electronic steering. So you can electronically steer the view angle of the antenna with a very high capacity. It has no moving parts, it is conformal, it has less drag, lower fuel consumption, and you will save about 2% of the fuel saving in US dollars. That's about $140,000 savings per plane per year. So how does it work? So let's go to a conventional phased array antenna. This is a conventional phased array antenna. It has a very narrow band, and you can tune it, and then it will give a tunable beam, in this case. If you want to have it broadband, so more frequencies, in this case, for example, using the KU band, that is a band of 10 gigahertz to 12 gigahertz, a satellite communication band. You use 4 different frequencies, for example. So red being the highest frequency. Well, if the plane starts to move, then you need to point and track the satellite. So you need to be able to look at that same angle with all frequencies. But what happens with this phased array antenna? Different frequencies will look at a different angle. And we call that beam squint. So that is limiting the bandwidth of your communication. And not only for satellite communication, but also then for 5G communication. So what we need is a different time of tuning. And we call that true time delay. And that's what I'm going to explain. But the effect here is that with the true time delay tuner, you can do it broadband. And all frequencies will point at the same angle. Which means we received broadband with a wide view angle. Well, a little bit of technology then. If you take an antenna, in this case you have antenna elements, and you have a tunable true time delay. If there's no delay, all antenna elements radiate equally, and you will get a certain wavefront and a direction of signal propagation. If you then start to tune each antenna element with a different delay, then effectively you start to tune the direction. And that is what we can do continuously. You can also use it as a local hotspot. So you take another delay per antenna element, and then you create a focal hotspot. So you can track, you can tune, you can focus, you can continuously optimize your signal towards your device or towards your group of users. So one level lower, towards the optical chip is how the photonic beam forming principle works. In this case, we have broadside reception. So we have a signal coming from the satellite, and it's coming into it's converted from RF to photonics, and then there's delay items that are set off, and with this type of configuration, we see we optimize for broadside reception, so there's no delay. But now we can start to introduce, in the green particles, in the green sets, we can start to introduce a delay. And in that side, in that case, we will be looking at a different angle. So we have a fixed delay for the first branch, and the second delay for the second branch, and for the third, and so on. And in this case, we combine all the signals in phase, being the effect of the view angle in a tilted direction. And we can continuously tune these delays in photonics. And that is very unique. So we have manufactured several of those chips at the left-hand side. Those are about 1 by 2 centimeters in size. And the example I've shown there as a chip is a 16 antenna element to 1 beam converter. So, but we can do it also in a multi-beam system. So this is a little bit more complicated. You have the same antenna array, also with delays for beam steering, but we have coming from the left 4 or 6 or 8 or 10 or 36 different beams. And if they move towards the chain, they come at the antenna elements, are delayed, and you can do the similar type of steering with tuning the individual elements. So for the orange one, the green one, the blue one, you can do the same, and you can do the settings a little bit similar, so you can come up with a multi-beam system. And even with double frequencies used. So we can also put next to the orange one a blue one. And we've also manufactured that one, and that's about 3 by 2 centimeters in size, that chip. So that's our first prototype. So this was built on a research we did together with Airbus to create a multi-beam satellite to get multi-beam coverage over the Earth. And this is the type of coverage that you can get then for 1 terabit per second capacity. So for example, at the left-hand side, you can cover Europe with 1 beam, but you can also break it up in multiple beams. In fact, on the middle one, you can use many spot beams and then also reuse the frequency for different areas. So which means another 30 times increase of the potential capacity. You can use it also as linguistic beams for Spain, for France, for Germany, for Scandinavia, and also for very local narrow beams here in Asia. So then another application next to satellite communication and avionics is of course the beamforming network for next generation terrestrial networks called 5G. And this picture you've seen before. What it is, we have an optical beamforming network, so that's the chip that I showed. And the advantages of this is that it is dynamically and continuously steerable beam. It's an adjustable beam in shape and beam profile. And we can also have active interference suppression to have noises out of our path. It has very large bandwidth, can be achieved, and it can achieve very large view angles. And we can also do the multi-beaming, as we showed. So this technology is scalable also from 1 to 100 gigahertz, because we do it in photonics. It has very low power consumption, and the technology is also scalable. It's all based on a small chip, on a silicon-based chip. So we are now ready for startup to mass volume since the participation of YMK Photonics in our company and our established volume production site here in Korea. So a typical coverage you want to have for next generation networks is also about 1 terabit per second per square kilometer. So that's where a lot of antennas are used, are required, a huge infrastructure of base stations, and the combination with SATCOM to get that done. So in summary, for wireless networks need beamforming to make it efficient, effective, and cost-effective, affordable, and economic. So the Internet of Things, virtual reality, and augmented reality require a robust wireless network to connect the 50 billion devices by 2020. Need to provide worldwide coverage, high speed and capacity, low latency, and being able to support continuous high growth. Photonics can disrupt the wireless infrastructure with true time delay beamforming technology, as I have presented here. Photonics is an enabling technology, and fiber networks are already based on photonics. So photonics enables the true time delays instead of replacing the phase shifters that are used in conventional technology, which gives us the opportunity to address larger bandwidth applications at large view angles. We can do continuous tuning in photonics for real-time signal tracking and simultaneously multi-beam capability for efficient coverage and frequency reuse in satellite communications. So those are the main takeaways from what you can do in photonics, what we have achieved, and how we make VR, AR possible, and how you need to rely on a robust network. Thank you very much for your attention.